Hello, everyone. Welcome to our global webinar series brought to you by Rockflow Dynamics. My name is Jessica Kalin from the Rockflow Dynamics Calgary office, and with me today is Senior Reservoir Engineer Nestor Hernandez to present to you Geomechanics in tNavigator. We would like to thank each and every one of you for joining us today. We are honored you're able to give us 30 minutes of your time for this webinar. These are new worlds we're navigating, and our RFD team is working around the clock to maintain and increase support for our clients. Despite the global changes, we continue to be there for you 24/7. During today's webinar session, all of our attendees' microphones have been automatically muted. Should you have any questions, please navigate to the questions pane on the right-hand side of your control panel. At the end of this session, we'll be addressing as many of these questions as we can, the remainder of which will be answered and posted online for your reference in the coming days. Additionally, this webinar is being recorded and will be uploaded to our RFD Europe YouTube page, as well as uploaded to your FTP folder on our support website. Should you be left with any questions at all, or if you have a suggestion on what you'd like to see in a future webinar, please contact us at asktnav@rfdyn.com. The email address can be found at the bottom of this page. Each webinar in this global webinar series covers a breadth of topics from geomechanics to cloud computing to hydraulic fractures and well placement optimization. The complete list can be found here, on our LinkedIn page, as well as on the main GoToWebinar registration page. Each of our webinars touch upon a different aspect within the integrated reservoir modeling process available in tNavigator. If you're interested in learning more about the complete workflow or would like to start a free trial, contact us at asktnav@rfdyn.com. Now for today, we are live from Calgary, Alberta, and I would like to introduce you to Senior Reservoir Engineer Nestor Hernandez. My apologies, we're having some technical difficulties.
Technical difficulties on my side. Jessica, could you confirm that you are listening?
Yep, you're all connected now.
Okay, thank you very much. I lost connection for a minute here. So today we are going to be talking about geomechanics in tNavigator. My name is Nestor Hernandez, and I'm in Calgary, Alberta. Also, at the end of the presentation, my colleague Eddie Evans, who is from Houston office, will be helping us to answer some of the questions. So our agenda for today is here on the screen. We'll start with an introduction, and then we'll go through which are the types of geomechanical coupling. Then we will describe what we call the joint system of equations. We will show how to set up a model for geomechanics and reservoir couple modeling. And we will go through some examples and conclusions at the end. I have to say in this webinar, I will be using the simulation module, but also Model Designer can be used to create models, couple models with geomechanics. All the functionalities are already there. So let's talk a little bit about porosity and permeability changes based on geomechanical conditions. Compaction and subsidence is very popular in shallow water, for example, like the uh, the uh, the south coast of the US and also in Lake Maracaibo in Venezuela. This is very important. Also, in many applications to study casing damage risk and for reactivation, these two are more or less related. And in Canada, for example, it's very important to study cap rock integrity. And now with the unconventional industry pushing forward, fracture propagation is a main topic for geomechanics and resource simulation. Now, how is this being done over time? Well, in classical dynamic resource simulators, the geomechanics is approximated by changes in porosity and permeability induced by rock compressibility. And that could be a constant or a pressure-dependent value. During depletion and injection, the stress field can change, resulting in various rock movements like compaction, induced fracturing, and enhancement of natural fractures, and fold reactivation. Also, the rock movement has direction, and it could affect permeabilities and fault transmissibility in addition to porosity changes. Hence, the scalar pressure-dependent rock compressibility may not be enough. So that's why sometimes it becomes essential to connect reservoir flow and in situ stress to perform couple simulations. Now, how to do that? Well, there are different ways to do that. The classical approach, as described earlier, is to model pore volume changes induced by rock compressibility. What we call then the extended classical approach would be when that rock compressibility is pressure dependent, like in a table form. The first trial to couple with a geomechanical simulator can be done in one-way coupling, where the pressure that's calculated by the reservoir simulator is fed into another engine, a geomechanical engine, to get the stress and displacement. But this is a single time snapshot of those values, so there's no feedback really. Then we can go into what is called the loose or leapfrog, which is the most typical coupling that is in the industry right now, which is when the reservoir simulation feeds pressure to the geomechanical engine, and the geomechanical engine calculates porosity and sends the porosity back to the reservoir simulator, and the reservoir simulator, basically the model is restarted with this new porosity and run another time step, and then it gets another pressure and goes back to the geomechanical. So it's like a going back and forth between two simulators. That requires two simulators and one interface to create that process. Now, what we are proposing here and what we have already implemented is what we call fully coupled. I'm going to describe that. To achieve fully coupled, what we have to do is to create a joint system of equations. What is that? Well, it's when all unknowns like displacement, pressure, concentrations are solved simultaneously. This is described in a SP paper that you can see there on your screen. And it's basically what you see on the screen is just writing the flow in porous media equation together with the rock mass conservation equation, the equation for linear elastic media, and the mass conservation inside porous media. And all this is a system of equations that will be solved simultaneously. There's a couple of boundary conditions. One is for displacement and the other is for stress. On top of that, as we solve these equations and we get enough information from them, like for example the stress field, we can calculate things like the Moore-Coulomb failure criteria that will tell us when a grid block is more likely to fail due to the stress field that's been applied to it. We also have another criteria, it's called the Barton-Bandis, and it's very similar to the Moore-Coulomb, just that it uses two different coefficients that have to be supplied to the model to get the answer. Now this provides some very important unique features. Number one is one single grid. The same grid is used for reservoir and geomechanics simulations, block center for reservoir simulation, and block corners for geomechanics. it is one solution, it means that the joint system of equations are solved in parallel and simultaneously. Geomechanics are solved in CPU cores. Reservoir dynamics are solved in CPU and GPU cores. All model types are supported: black oil, thermal, and composition. And also this calculation is supported in clusters. Also, permeability can be stress dependent. Permeability can be defined as a function of minimal and maximal stress. And this is basically a table. And the keyword is called permstat. Now, setting up the model is pretty simple. I'm going to show here an example on how to do it in the dataset, but the same setup can be done in Model Designer. So basically, there are 5 steps here on the screen, but the only ones that we require to run geomechanics are the first 2. The other 3 steps are optional. So it's very simple. Just the first step is to activate geomechanics in your run spec section, and it's a single keyword. And the second step is to enter Young modulus and Poisson ratio in your grid properties, and those are entered like any other grid properties that you could have, like porosity, permeability. Is the same way to enter these properties. You just need to get the values from the geomechanical studies or from a geophysicist in your company or any consultant. Then there's other options that could be added, like for example specifying parameters for the failure criterion, or we can enter the permeability multiplier versus stress table, and we can enter as well the stress and displacement boundary conditions. So it's just any existing model dataset can be modified to create that. And we can also import an existing model into Model Designer and enter these parameters in Model Designer and then export for simulation.
Wonderful. Thank you, Nestor, for giving us an overview of using fully coupled geomechanics in tNavigator. Now we want to stop and do a quick poll of the audience to better understand the application of geomechanics within our community. On your screen, you should now see a pop-up with the poll asking you, which is the most likely application for fully coupled geomechanics within your team, as well as 5 options to choose from: dilation compaction, casing damage risk, fault reactivation, cap rock integrity, and fracture propagation. I'm going to leave this open for about 30 seconds. Please choose which best applies to you. Ten more seconds. I can see the polls are still coming in. All right. Wonderful. Thank you to everyone who took a moment to respond to that poll. It looks like the majority of you say the most likely application for fully coupled geomechanics in your office is fracture propagation, although dilation compaction is closely behind. So if you would like more information on your preferred application method, please reach out to your local support or reach out to us at asktnav@rfdyn.com. Back to you, Nestor.
Thank you, Jessica. Very interesting results, and it will help us a lot to get our developers to work on those special features. So let's move on. Now I'm going to show some examples, and for that I have a video, and I will be describing what's happening in this video. So let me open here. So firstly, we are going to open an example that has a basic setup, just to see what properties can we visualize and what are the results. And these models are from the tutorials that you have available, so feel free please to try and give us feedback. So let's open this model. When you open the model, first thing you will notice is that there are some new messages that are in color blue, and these correspond to the active blocks for geomechanics. And if you notice, the total number of active blocks would be 6 times the total number of active blocks for reservoir calculations. And that's because every grid block is being divided into 6 tetrahedron for geomechanical calculations. Now let's have a look to the keywords in the dataset. We have this keyword that activates the geomechanics in the run spec section, and then we have a couple of keywords to enter the geomodulus and Poisson ratio values in the grid section. That's all it has. Then we can also visualize those properties here in our initial properties, like for example the geomechanical active grid blocks, the geomodulus, and the Poisson ratio as well. In terms of calculated variables, we have some new variables here. For example, notice that the porosity now is a calculated variable, it's no longer an initial variable. And if we run the model, we could see that the porosity is changing with time. This is not pore volume multiplier, it's actual porosity changing with time. That's a result from geomechanical calculations. As you can see, this model will run as any other model runs. Nothing special really. You will see the log going and the model running as normal. Let's zoom in and see a little bit here at the porosity details. You can see that now the histogram of porosity shows changes that were caused by geomechanics. We can visualize those changes as well in 2D view, and if we do color by contour lines, we'll see clearly how that porosity has changed at the end of the run. Another things we can visualize here in geomechanical runs are the displacement vector, which can be seen both in magnitude with the colors and in direction with those arrows that you see on the screen. Those arrows can be adjusted by size with this slider. It's very useful for visualization. We can also see maximum stress results with magnitude and direction, and minimum stress results, magnitude and direction. Let's have a look in 3D as well for maximum stress. And as you would expect, because this model is very simple, it has just one injector and 3 producers, the stress are reflective of the pressure that's being caused by the injection of this injector wall. So those two properties should have a reasonable match. Let me do something else. Let me create here a cross section that's connecting this producer with this injector here in the model. Now I'm going to close this window here, move to 2D, select cross section, and let me show displacement vector and color by grid. And now you can see in 2D cross section how the displacement is changing across those two wells, and we can adjust the vectors in 2D as well. So it's very intuitive, it's very graphical, and it provides a lot of information. Now let's have a look at the case that has the more column option activated. So I'm going to open another model here that has those keywords already entered, and let's have a look at the data set. So the only new thing you'll see is this rock fail keyword there that's activating the calculation, and then the 2 properties that are required, the cohesion and the angle of internal friction. Those things can be also found in our initial properties. You hear the angle of internal friction and the cohesion value. And we also have a new variable called rock fault, and this property will tell us where are the grid blocks that are failing. I'm going to create a cut with that property. So basically I'm going to select here the menu, and when this property equals 1, means that the rock is failing. It will show in red color. And now let me auto update this filter and run the model with the active cut. And at the beginning you will see there's nothing around the injector there, it's all blue. But as soon as I start injecting and the pressure goes up, the stress is so high that it's basically causing those grid blocks to fail. Basically what's happening is that we are hydrofracking that injector well with the high injection rate and high pressure that has in the bottom hole. So it's going beyond the Morcon-Long criteria. We can also show, of course, in this model, it's like any other model in geomechanics, we can show stress, stress field, and we could also see porosity changes versus time in this model. Let's see another example. It's a very interesting feature. It's called roof deformation. So for that, I'm going to open another model. And this model, the only special thing that has, in addition, is a boundary condition for displacement. So if we look at the data set, it's the same. We activate geomechanics. There are some geomechanical properties that are specified. And at the end, we have the boundary condition that we want to apply into this model. So let me show how it works in a simulation here. So if we go now in vector fields, I'm going to show displacement vector, because what I want to see is how the rock is moving. But also, we are going to add this feature called roof deformation. It's like a surface. And when we run the model, we'll see that that surface is changing as the model is running. And it's changing proportionally to the displacement, basically. So it tells me that in the injector, there's a heave on the roof caused by the increased stress, and on the producer, there's subsidence of the roof because of the lower pressure around the producers. This surface can also be adjusted like the vectors did with the same slider, and it's a very nice feature to visualize changes in deformation in your model. So with that, this is the end of the video. Let me go back to my slides. Common question that we get is, can this be applied to more complex cases? So we have tested a few of them. For example, here we have the very famous SP10 model, where we just enter Young modulus and Poisson ratio and activated the geomechanical option and run the model. It takes probably 1 minute to convert this model to geomechanics, and then we can visualize already a very heterogeneous displacement vector, I would say, in the SP10. We have some other models like this one, that shows gas production from a tight sand. It's a model with complex logarithmic LGRs. It's a three-phase model, 150,000 active grid blocks. Fracture zone is 1 Darcy, fracture width 0.15 feet, NFC perm is 0.1 millidarcy, half length is more than 300 feet. When we, in this model, visualize the evolution of stress versus time, we can see that after a month, the stress is relatively small, but after, say, 6 months, even 3 years, we can see a very important change on the stress. And it's because in tight formations, especially low permeability formations, we have a huge drawdown between the reservoir pressure and the pressure at the well because of the low permeability, and that causes a lot of stress in the rock around those fractures. We can also see evolution of absolute displacement in those cases, and as well, it's a very important magnitude change most of the cases. One very interesting model that we have is this compositional model with 19 components. In this case, we are visualizing displacement vector in 3D. And let me describe here a little bit this model. It has a series of water injectors on the edge, and on the anticline, we have maybe 20 producers there. And there's a fall going through this model at the top there. If we see this model in a 2D view, and when we plot the stress tensor, we can see very interesting features. Like here again, we can see the role of peripheral injectors here, water injectors, and then we have the producers at the top of the structure. You see not much is happening in terms of stress because the blue color on the edges of the pool, but as we approach the oil zone, there's a huge change of stress in between the injectors and the first row of producers. But most importantly, we can recognize here in the middle a red zone, which is at the tip of that fault that's existing in the model. And this raises a bunch of flags. For example, we could be in the case of, if we run this, for example, with a failure criterion like Mort-Coulomb, we could probably find blocks that are failing on Mort-Coulomb, which means that this fault could be either reactivating or even growing. This fracture fault could be growing because of the stress field being applied, and that has big implications. If this is a populated area, that could be causing microseismic events that could cause some issues with the community. And also, more importantly, probably these wells that are nearby the fault could be suffering of casing damage. So obviously this is not a definite answer. It's a model and it needs to be correlated with field data, but this is so simple that why not do this if it's going to raise some important flags that we can then probably trigger a bigger study, a more detailed study in terms of the effects of geomechanics in our field. So that's a very interesting example, and with that I want to conclude this presentation. In summary, today we cover what is fully coupled geomechanics. That's an industry first field implicit and fully coupled solution that offers unique capabilities. It's very easy to set up. You can do it in simulation, in the text file, or in Model Designer. You just need to activate it, then enter the main geomechanical parameters, and then the model is ready to go. And it's available. It is another complementary feature, and it comes with the basic Blackwell license and no additional cost for the customer.
Wonderful. Thank you so much, Nestor, for the presentation, and thank you everyone for your time and attention today. For your reference, this webinar was recorded and it will be up on the RFD Europe YouTube channel probably tomorrow. We'll now take a final few minutes to answer any questions from the audience. Any remaining questions we don't have time for, we will be sure to answer after this session and post online for your reference. So if you have any questions now, please go to the questions pane. And I'm going to hand it over to Eddie Evans from our Houston office, who will start answering the first couple of questions. Eddie?
Hi, thanks, Jessica. Let me go through some of the questions real quick, and I'll see one that may be good to answer that can answer multiple at the same time. One of them is can this be used to predict fracture propagation? That's actually a really good question. Currently, tNavigator Geomechanics considers the elastic regime only. So, for example, the Moore-Coulomb or Barton-Bandis criteria could provide information fracture initiation. Meanwhile, our developers are also currently working on improving the functionality to expand applications into fracture propagations for unconventionals. There's also, does geomechanics make the run go slower? So that's also pretty good questions. The simulation runtime is impacted because there are more unknowns and more equations to solve for each grid block. That being said, it's also expected that a fully coupled geomechanics solution like tNavigator will deliver a faster and more accurate result than the current kind of leapfrog one-way and two-way coupling method used by most other software in the industry. So
I'm going to cut you off there, Eddie. We're just out of time. I realize we're at 32 minutes past. So thank you everyone again for your attention today. Stay safe, stay healthy, and we hope to see you at our next webinar on Tuesday morning. Thank you very much, everyone.